Okay, so we're going to start with our first topic of analysis for reinforced concrete. And so let's talk about the principles of reinforced concrete. Okay, first of all, I'm going to talk about flexure principles. So first of all, let's talk about kinematics. And kinematics just has to do with geometry. So we're just going to talk about the geometry of reinforced concrete beams as they bend. And so the first thing is plane sections remain plane. So if you see me write down PSRP, it's shorthand for plane sections remain plane. And what happens is that when you bend a beam, if you were to mark it with these vertical lines like this, when it bends, those vertical lines remain straight. And so this was plane, and now the section is still plane. The plane section remained plane. I've drawn it for a relatively small deflection here. Well, reasonably small. Plane sections remain plane even up to failure. So this is a good assumption. What this means, if plane sections remain plane, is that this change in length, it's getting bigger as you go down. It's getting bigger linearly because they're straight lines. So that means the strain is linear with depth. So here's a strain, and it's linear. Okay, so it's not shaped like that or curved in any way, it's straight. Okay, and the top of the beam compresses, the bottom of the beam stretches, and so somewhere in the middle, it's not changing length at all, and that's called the neutral axis. What we're also going to assume in this class is when the compression concrete fails, the strain is 0.003 or 3,000 microstrains. Micro means divide by a million. Okay, so at failure, the strain of concrete is 0.003, and the strain is linear with depth. One other thing that I want to point out is if you take this angle, okay, so let's call this y, and that's epsilon. That angle is epsilon over y. That angle there is the curvature. Okay, the curvature is it's approximately equal to, for small deflections, the second derivative of the deflection of the beam. The other thing the curvature is 1 over the radius of the deflected shape. So if you had a beam like this and you did that, if it was bent to a circular arc, that radius, okay, 1 over that radius equals the curvature, which is the strain over y. And the units work out, right? This is distance, no units. Strain does not have units. Okay, so plane sections remain plane, which means the curvature is 1 over rho is equal to the slope of the strain diagram, and that's approximately equal to the second derivative of the shape of the beam. Okay, next, let's talk about internal forces and equilibrium. Okay, when you have a beam with steel on one side only, and you bend it, so in this case, we'll put compression on the top, tension on the bottom. Remember, the strains are linear with depth. So the strains are going to do something like this. Okay, that's strain. And then this is compression. Down here is tension. What we're going to do is we're going to take the stress strain diagram. So here the strain is 0. Here the strain is a certain amount. Here's another amount of strain. You read all these strain values, and then you would get the stress values. And so if you convert the strain into stress, this picture here just gets flipped onto there. So that's what the stresses would look like in the compression zone of the beam. Down here is our first assumption. We're going to say concrete has no tensile strength, which means there's not some stress down here due to tension, okay? There's no tensile stress below the neutral axis in the concrete. However, what will happen is the steel will stretch and it will be in tension, okay? And that rebar will have a force, okay? And again, no tension, concrete tension force because it's cracked, and there's going to be tension in the steel. So we have tension in the steel, and we have compression in the concrete. And the concrete is going to look like, the stress in the concrete will look like the stress strain curve. Okay, so if you could get the total force of that concrete stress distribution, turn it into a compressive force, and you get the stresses in the rebar and multiply them by the area, you can get a tensile force. By statics, summing forces in the x direction, C has to equal T, right? Then they can't have to add up to 0. And you've learned about this from dynamics and from statics. Whenever you have two equal and opposite forces that are parallel, that's called a couple. And the moment due to a couple is just either force times the lever arm between them, Z. We're going to call that Z. So the moment, Mn, that's being applied to the beam is resisted by this compression and tension couple. And that will be just T times Z or C times Z. They're the same because T equals C. Okay, how do we handle these weird concrete stresses that look kind of like a parabola? Okay. What we're going to do, we're going to replace the parabola with a rectangle. And the reason for that is we need to get this area and we need to get the centroid, because we're going to replace the distribution with a compressive force, and that's going to equal to the area of that times the width of the beam. And we need to put it at the centroid of that parabola. Now, the area of a parabola, well, it's not even exactly a parabola. The area of that curved shape and the centroid of that curved shape is difficult to deal with. However, this is called the Whitney stress block. Everybody knows the area of a rectangle, right? If that's the base, that's the height. The area is just base times height. And the centroid of a rectangle is just halfway up, h over 2. So what we want to do is find a rectangle here that has the same area and centroid of this parabolic shape here. And the way you do that is you make the rectangle sit a little bit above the neutral axis, okay? And this will work out. It's actually got a lower height, and it's a little bit above the neutral axis. So exactly what do we do? We'll get to that. No, I'll cheat. I'll just tell you. If this is f prime c, this height here is 0.85 f prime c, and this height here is beta 1 c, and beta 1 is a variable, but often it's coincidentally also 0.85 c. So this rectangle here would have the same area as this parabola there, and the centroid of that rectangle would line up with the centroid of that parabola. Okay, let's talk about the rebar stresses. They're going to be something we call elastic plastic. Okay, if the strain in the rebar is above the yield strain, we're just going to say the stress is equal to Fy, and usually the strain is above that. And so let me draw a picture of what it looks like. So here's strain, here's stress. Remember, we have to use F in this class. At first, it's linear. The slope is E until you hit epsilon y. And after epsilon y, it's constant at Fy. Okay, so it's almost always, the steel is almost always out here. So the easiest thing to do is assume the steel stress is Fy. From equilibrium, you're going to get the neutral axis C. And then once you get C, you can determine the strain in the steel and just make sure that's bigger than the yield strain. So what I mean by this is you will find from equilibrium this neutral axis C. You know that the strain in the concrete at the failure point is 003. Remember, we memorized that. And if by similar triangles, you could get the strain down here in the steel. Okay, so you get this number and make sure it's greater than epsilon y, which is Fy over E. It's 0.00207. I've done it so many times. If you take 60 KSI divided by 29,000 KSI for E, that comes to 0.00207. Okay,